So this is actually, although Vicente and myself are talking, this is actually a whole team effort. It's not just me and Vicente. In fact, it's mostly not me. There's Lois, and there's Maurizio, and there's Brian, and there's a whole team effort here doing this. And this is actually quite interesting. I didn't realize when I was doing this presentation how deep you can go into constants and go down the rabbit hole of just this area. So there's another rabbit hole for lawyers, if you want to. But that's more interesting. This is from Jeff Dinkins, the resident Duke artist. So this is Duke encrusted in amber. Think of bejeweled constants in your constant pool. And don't mistake this for thinking that Java is trapped in the past in time. It's certainly not. As you see in this conference, Java is very much moving forward in very interesting ways. So the goals of this is really to enhance the definition, declaration, use of constants in the whole Java platform. It's a nice vertical slice through hotspot, for libraries, and through the language, and through Java-C and stuff like that. So at runtime, we want to dynamically declare any constant value in the constant pool of a class file and usually reference those values lazily, like we can do with some constants today. And we want to do the same for language. We want to declare rich constants, fold them, and use these so we can have language level support for what we have at bytecode, which is load constants, LDC, or actually put in the language InvokeDynamic. How many people would want InvokeDynamic in the language? Remy? Remy wants it. I do. LDC is interesting too. So if we can up the level and do this in the Java language, it's not for everybody, but it's for a core set of Java developers. This, I think, will become very interesting, and they'll start using it in interesting ways. So here's the runtime code. So it's Project Amber, hence Duke trapped in amber. I shouldn't say trapped, encrusted, bejeweled in amber. So if you want to get the code, you can do this HG incantation and switch to the Condi branch. Build it and make it. So it's all, what I'm going to talk about is actually implemented there, and you can play around with it. And if you're interested, I really do encourage you to do this. And there's other, we'll get to the bit of the language side later, but Amber has a bunch of branches with a bunch of separate projects like local variable type inference, pattern matching, Brian will talk about, and stuff like this. A lot of activity going on in this code base. So a bit of the past of what can we do with values today. So there are about 3 areas where we can reference constant values today in the bytecode and at runtime. So one of them is static field initialization with constant value attribute. This feels like a bit of an anachronism to me in the bytecode, a little bit the way it works. There's also the instructions, the LDC instruction, and LDC2, and that points to the limits we have in the bytecode we have today, which is 2 to the 32. We can't reference more than those in the constant pool. I'm not going to directly address that today. And of course, we have the special LDC2W just for longs and doubles, because they're kind of special and annoying when you write stuff, because I always forget that they're double slots and my code crashes first time. And then we have Bootstrap method arguments, so you can actually reference constants in the static arguments that you pass to InvokeDynamic. There's actually also other bytecodes that reference constants, and those constants are directly embedded in the bytecode instructions when you push values onto the stack. So there's actually embedded in the instructions there, but we're not going to talk about those. So we have a bunch of constant types that are supported. We have about 1, 2, 3, 4, 5, 6, 8 of them. They map to stuff in the Java language. So for example, constant class maps to JavaLang class, so forth like that. Some constants are actually resolved. They require work to take it from symbolic information and transform it into a Java instance, and that's where errors can occur because a class might not be found, it might be ill-formed, and you can do it for method handle, method type, where it has a bunch of classes, so one of those classes might fail, and then a method handle has a target type method, which takes a method type, and a method handle might be invoked static, invoked virtual, and failure can happen there too when linking, so forth like that. The interesting thing is constant integer. We can't represent byte or char directly in the bytecode, so int is used to represent narrower forms, and also the Boolean value, the 0 or 1 there. So if we look at what areas can use these constants, we see this constant value, which is used for static fields. It can only represent, sort of reference primitive values. It's very tied with Java-C if you're ever familiar. If you use static final, int x equals 1, you'll see, if you look at Java P output, you'll see this attribute being used there. This is something that John Rose talked about containment, and this is where I get my hook in here, that these values here are not necessarily contained within the compilation unit. They tend to leak across compilation units and cause binary compatibility issues, and I don't think we should use these going forward to try and stuff in other things in here. We should just leave it and park it off to the side and leave it gently on its own. Whereas all the others, they can reference these values here, but I note that LDC can't load a byte, can't load a char, and the same for Bootstrap method arguments. It's kind of restricted. So these 8 types here, it's very restricted, and when people start doing stuff, they tend to more complicated stuff. What do they use to encode stuff? The only thing they can use with a sort of variable length is string here. So they'll start sort of funneling things through string. You can encode anything in a string, UTF-8 string if you want to, but it can be pretty ugly and hair-raisy, base 64 it and so forth like that. So you tend to stringify things. So this is not a great state of affairs, but you can work around it if you want to, if you hold your nose. So it's very limited. You see what we have here, both in types, essentially in arity, I'll get onto in a moment, and resolution control. So constant values are limited to 8 Java types, as we saw. So therefore, LDC is limited. Therefore, Bootstrap method arguments are limited. Therefore, Indy is limited. Let's remove this limitation here. Also of note is that the Bootstrap method arguments we have when we do an InvokeDynamic is limited to 255 minus your method handle receiver, minus your lookup, plus your name, and plus your type. Let's get rid of that too. John did a sweep through the spec and just blasted that one array away recently. So we should be able to have as many arguments as possible, and even get over the limit of the restriction on the number of arguments in a method call as well by packing stuff into a varargs array if we want to as well. And also note there's no control over resolution of your Bootstrap method arguments here. When you get called, all stuff is resolved or it's an error. You have no control to say, I want to control the resolution of these things later on and control the way I do the error. You don't get a choice there as well. So it's pretty limited in terms of types, arity, and resolution control. And what about this? There's a whole bunch of stuff we cannot represent in the constant pool. What about int.class? How many know that int.class can't be represented in the constant pool? If you don't know, I'd urge you to compile and see what Java-C does. It's kind of interesting. I didn't know at first, and I looked at, oh gosh, goodness me, look at Java-C's code having to do that. So there's also true, false, bytes, shorts, and so forth, a bunch of stuff. But there's also enums. We're blocked. Thread state.blocked cannot be represented in the constant pool if you actually want to use that type in the constant pool. There's regex patterns. We can't represent those. We can't use var handles in a constant pool that I wanted to do. And in general, we can't call any sort of factory method that we might want to. It returns something a constant. And we can't sort of compose method handle chains with constants as well. So there's 2 generalizations here that we might want to do. So what about just use static final fields? That's kind of what we do today. This is an example of var handle in counted completer. So what we do is in our static initialization block, we look up the var handle and assign it to a static final field. And then in the code, add to pending count, we actually reference that static final field and do some work on it. But that's not lazy. At class initialization time, we do work here. That's costly. And there's a whole ceremony and setup here where things can go wrong. And if there's a bunch of stuff going on here, if you're looking at multiple handles, you might not use them all at once. So there's a cost, a performance cost to startup that could be amortized over time when you use these things if they're lazier. So Doug Lee hates this code. He just holds his nose when he writes it. Can we do better? Yes, we can. We can make Doug Lee hold his nose even longer. What you do is you stuff it in a static inner class to make it lazy. But that's equally as horrible as well. You really don't want to be writing this kind of code. So the idea is what you want to do is somehow LDC this var handle given some static arguments and then just call the method so it's lazy when you use it. We wanted to do this with the var handles jet, but we didn't want to go all the way to putting just var handles in the constant pool. That's a lot of work. We should be able to do something better here. And Vicente will talk about this and say how it's done in using the language instead. So here's another what if. What if you had a complex Java source expression that could be compiled into a group of constants which are then resolved on demand? It sounds abstract, but I don't think that's a theoretical question, because what Brian will talk about with pattern matching and switch expressions is pushing on this button quite a lot here. And we think we can leverage the constants, constant dynamic that we're going to talk about with pattern matching and do something really quite interesting. We could do this just using InvokeDynamic. Why can't we just use InvokeDynamic with constants? So we have a constant InvokeDynamic with a specific Bootstrap method we define, returning a constant call site, holding a method handle, accepting no arguments, so an invoke returns a constant value of the specified return type. That is a mouthful. It sort of suggests there's a smell there. They're not really first-class members of the constant pool. You can roll this yourself, and there's a blurry semantics here. Should LDC reference the constant InvokeDynamic? Can Bootstrap method arguments do it? It's kind of smelly. We need to up-level this and make it more fundamental concept. So here in enter ConstantDynamic. So it's a new constant pool entry in the constant pool. We've assigned it tag number 17. Now, if you are aware of the tags that exist already in the constant pool, 17 sits between either method type or method handle, I can't remember, and InvokeDynamic. There was a slot reserved for this already a couple of years ago. Some people in the InvokeDynamic group were really smart, saying they wanted this, but they just didn't have time to do it. Maybe if they had time, method handle and method type wouldn't exist directly in the constant pool. We would be using Condy instead. So this is trade-offs in terms of time and implementation here. So ConstantDynamic is to InvokeDynamic as field descriptor is to method descriptor. We're leveraging the name and type, but the name, the type in there is a field descriptor instead of a method descriptor. And we can reference it by LDC or a Bootstrap method arguments, including those in ConstantDynamic. So we essentially can get sort of recursive references going on here. So the Bootstrap method can represent int.class and so forth like that. So if I just go back to here, we see we want to reference int.class. If we're looking for a var handle to an int field, int.class has to be represented as a constant dynamic because we can't represent it directly. So what about Bootstrap method invocation? So we've improved this, so it's essentially equivalent to invoke with argument semantics, which is like invoke with an as type, but with no polymorphic transformation here. So essentially it allows us to support an unlimited set of arguments within constant pool limits. So Bootstrap method invocation, you don't know, is driven by arity and var args only, really. It's not explicitly typed to the name and type, and this enables quite a lot of reuse when you're using Bootstrap methods. So if we look at this table here, we can see a bunch of examples that I extracted out from the Java doc of the types of shapes or signatures of Bootstrap methods you can have. You can have a Bootstrap method for InvokeDynamic that basically takes a var args of args, and it will stuff in a lookup name and type, or you can explicitly mention those in the first one and have var args at the end, or you can explicitly type the stuff that you want at the bottom like that. It's very, very flexible in how you invoke these things, and you have to return a call site back. And that could return object instead, and it just do runtime checks at the Java level. The VM doesn't care. So we can do the same for ConstantDynamic, and instead of returning a call site, we return an object, and the exact same types of signatures apply, except for the third argument here is not a method type, it's a class. It's the type or class of a constant you actually want to return back. And so that's it. So it's very, very similar. It slots in very nicely with Indy. And if you're feeling particularly advanced, you could actually use a BSM both for Condy and InvokeDynamic if you really want to. I wouldn't recommend it, but you could. So there's new signature forms we added for Bootstrap methods. So the first one is a Condy BSM, and we can actually, because we can now use Condy, we can use Condy itself to represent like enum constants in Bootstrap method arguments, for example, the threads.state I showed before. We can have a pattern like a regex constant and so forth like that. Same applies to Indy as well. We're up-leveling it, so Indy gets improvements too. We could return a char constant instead if we really wanted to. Or the latter one is something more interesting, which gets around the constraint on resolution, is we can have just two arguments. The arity is fixed to 2. The arity base, if the arity is 2, no var args, then it's a BootstrapCallInfo. And this allows us to pull constants from the Bootstrap method arguments and pull them on demand and resolve on demand rather than getting them all at once and creating a resolution error. And this gets more important, I think, if we're looking, say, at pattern matching and so forth like that, where we may not all cases in your switch or pattern switch will get hit, and you don't want to create a sort of resolution error for all of the switch statements up above when you're dealing with a pattern. You only want to create your resolution error when you hit the right case. So with this, we might be able to do that better. There's various ways we can do that, but this is one way to do it. So BootstrapCallInfo, as I said, is driven by arity. Let me just have a look at how much time I've got there. How much time do I have? Okay, I've got about 8. Can I speed up? It's driven by arity. So example here is pull BSM mode. So we look at the parameter count, it's 2, and it's not a var args. That's essentially the trick, what we're doing here. So that's that. And we pull, and the scope of resolution can be expanded beyond the method call. We could return the Bootstrap call info in something we're returning in our constant, which then can do the work later on. So we're going beyond the scope of the actual Bootstrap method call here in terms of resolution, which is maybe quite an interesting thing to control. So the constraints we have here is, here's the problem. Here's a gentleman's agreement we have in streams, and so forth like that John showed before. Well, we got a mutability problem in Java that obviously what is returned should be constant, but we can't actually enforce that. So there's a gentleman's agreement. It sort of rules out arrays naturally until we have frozen arrays. And also, you shouldn't be returning something like a modifiable collection, like array list and so forth like this. So you have to be very aware and careful of what you return. I think we really do need some form of immutability, better immutability in the platform. Perhaps that's frozen arrays. Perhaps that's a way to freeze array list as well. Perhaps that's persistent collections. Perhaps there's a way we can build up stuff in a thread or fiber-confined way, then freeze it and say this is a persistent collection. If you add stuff to it, then you don't do a full copy, you just do a little copy. There's lots of ways we can improve this story, but we can't actually control it. Maybe we could later on if we have some forms of detection, but we might need runtime checks as well, as John was saying. There's also limits in the name. Remember we said there's a name and type. There's a certain limitation in the field descriptor in terms of characters. You can't have certain characters. So you can't use that for all forms of regex expression if you want to pass a regex expression to pattern.compile constant or stuff like that. So you might have to use an extra additional parameter, so you have to be careful there. Yeah, that's what I said there. So there are a couple of constraints. And the Bootstrap method is deceptively simple to implement, but you really do have to be careful in terms of how you deal with exceptions, how you potentially deal with binary compatibility, and how you deal with security. We've been hit, I probably should be careful what I say, but we've been hit with a few interesting security issues with our own Bootstrap methods for InvokeDynamic. And it's probably the strongest security requirements for us in the JDK than outside the JDK, but you do have to be aware of this. It's deceptively simple to write, but you've got to be careful. And we also need an API to generate ConstantDynamic bytecode and or language support. Who wants to add ASM support for Condi? We also have Maurizio's bytecode API, which is super neat. I've been using that. But we do need something just even for testing, which is Vicente. There's another thing here is why don't we just, instead of using a Bootstrap method, can we represent a static method directly in our ConstantDynamic instead of a Bootstrap method and just call it with the arguments? We could do, but we think that using a BSM wrapper is actually almost as efficient in terms of bytecode savings. There's a little bit more boxing going on and so forth like this, but the cost of the VM up call and down again is probably going to be larger. So maybe this type of thing might depend on some performance analysis, I think, on what we do there. So we could short circuit BSMs, let any factory method become a method to return a constant, which is obviously has its own danger because it might not be a method that's been designed to return a constant. So you have to be careful with that too. There's just a few more constant types that we could add. We could add constant octets, which is a way to sort of say, here's a bunch of bytes. We could map that to near-byte buffer. And that might not be limited to the constraints of 2 to 32. It could be a whole section of bytes stuffed at the end of the class file and then mapped in. Stuff like that. There's a way we could group constants together as a stream of constants offset from those in the constant pool. It could be segmented constant pool aspects too, we could do that. And there's the interesting constant value or constant type, which you'll see Maurizio and others talk, I think Fred talk about in terms of how you represent value types, how you represent classes, value types, and unions of these things together. So you'll see that mentioned later on. And with that, I will hand over to Vicente.
Well, thank you very much. Yeah, well, so now we continue with the part of the changes in the language per se, which is more of the constant folding project, as we call it. And okay, before Paul was commenting about the repo where the Condi work is, and there is in the same Amber repo, there is a branch that somehow contains the changes for Condi plus the constant folding project, and we call it Condi folding. So these are the commands to clone the repo and build it. So what's the motivation for the constant folding project now? So basically Java is making an increased use of Indy now. So we see it in lambdas, there is a string concat, and there is more to come. And at the same time, I mean, right now we can invoke, we can use these facilities in Java code, but we have to go to reflection or bytecode spinning. And so this is kind of hard to test it. So you have a feature in the language that you can't really test really easy, no? So there is a very good example, which is the Indy test written by John Rose, and it's actually kind of complex. It's a very, very good example of how complex it can be to test this kind of I mean, InvokeDynamic. You can also use the dynamic invoker and in your code, but still, you won't be testing the same bits. No, there is no. If you use reflection, there is no actual InvokeDynamic in the bytecode. No? So this is an example of how it goes for testing Indy. I mean, in the using reflection, no? And we can see. I mean, all the steps we have to go, and this is kind of complex code and is very error prone. No? So you can make mistakes creating the method type or the method handle or passing the arguments. Actually, I mean, to write this test for the presentation, I have to go through several of those errors. No? So it's kind of easy to make mistakes. No? And again, I mean, you are not stressing the same code. So kind of the goals for the project were to, as Paul mentioned, to expose InvokeDynamic and LDC to Java developers. So and also this will expose Condi as a side effect. For example, it is possible to replace the initialization of an access of static field with an LDC. And to get to this, we define nominal descriptors that we call constables for constant pool entries. No? And the idea was that already existing constant could be also described, could be also considered constables. So we do that for integer and string, for example, that are considered constables in the projects. So what's the current support for constant expressions in Java? So we have basically primitive and string literals are considered constant expressions, and then combinations of them, and these are also considered constant expressions. But there are some limitations. For example, we can't represent stuff like method type directly using the language and have that actually be represented in the constant pool as a constant. And so first, we define the console interface. Very simple. It receives a lookup object, so it have access to check what code can create it. The consoles are fully nominal. There is no validation. There is no class loading. So they are really, really light. So the idea is that starting from that console class, we can define class constant, which implements console. And this is a very limited summarized definition of the class. We have a method to create the class constant. It's interesting here the trackable constant annotation. We'll talk about that later. And there are, as I was mentioning, there are also other constants. No? I mean, we have the method type constant, we have the method handle constant. They basically have some similar methods. No? In the case of method handle constant, we have all the flavors of static, of virtual, etc. to create different method handle constants. And as I was commenting, string also implements console of string, integer implements console of integer, etc. So we have defined new constant expressions in the language now. This part is interesting now. So we have that now an effectively final local variable can be considered, can be a console. No? So if you use it as an effective local variable, the compiler will track it, and if the compiler can prove that it's effectively final, it can use it as a constant expression. But we have limited the console to behave as constants only inside the compilation unit, because we didn't want binary compatibility implications with this, no? And there is no change to already existing constants like strings and primitives. So for example, if we want to create a class constant, we have this construction where we, I mean, you can define and say class constant of, which is the factory, and there is the descriptor, and the result is a class constant, and the compiler will track that class constant, that console, and we check all the use you make of it. No? There are also other constant expressions that we consider, and are instance methods. For example, in the second example, we have the same class constant we just create, and we can create an array of it, and that would be also another console. Or we can get a component if it is an array, and that component will also be a console. Of course, this means more work for the compiler. The compiler has to do more checks. You have to track and propagate all those new constant expressions. Remember the annotation I was talking about before. So if a method is annotated with that annotation, that will mean as a message to the compiler, okay, track me. And so the compiler has to do reflective invocation of those methods, obtain the constant, and start tracking it. Things can go wrong if the arguments, I mean, at some point you can have some invocations failing. This is, of course, reflective. And we have to check that all the arguments passed to an intrinsic method are all constant expressions. And also, as I was mentioning, new consoles can skip. I mean, can go beyond the borders of a compilation unit. That's another check the compiler has to do. No? So that means that a console, depending on how it's used, or not how, probably where it is used, it would be a console or no. Okay, consoles, but at some point we have to go to code generation. And so the idea to actually go to the code generation was to define a new class with two methods, InvokeDynamic and LDC, that the user has to explicitly use to actually tell the compiler, okay, I want an InvokeDynamic to be generated for this, and I want an LDC to be generated for this. No? So this is very explicit, no magic, and this is, for example, the definition for LDC. We have LDC receives a console, and the idea is to actually make this call to be intrinsified into an LDC and actually have that in the bytecode, with the restriction that the argument has to be a constant expression. It could be a string or primitive literal or a box of that. It could be a console, sorry. Or it could be an effective final variable pointing to one or the other. If the argument is not a constant, the compiler will issue a compiler error. So for example, we have here two very similar examples, but in one of them, I mean, the first variable C, local variable C, is effectively final. In the other case, we assign null to the variable, so it's not effectively final. And in that case, the compiler, when it sees the LDC, as it can prove that it's not effectively final, it will issue an error. This adds somehow a complexity, because I mean, the compiler can't prove that a variable is effectively final till it has done the flow analysis of the code. So the idea is that we are supposing, I mean, we're kind of assuming that this will be effectively final during attribution. Then after flow, now that we know what is effectively final and what is not, then we can prove if all LDCs are correct or no. The definition for InvokeDynamic is this is the definition in the intrinsics class. So we have a Bootstrap specifier argument, an invocation name, and an array of object arguments. Sorry. So the idea is that this should generate an InvokeDynamic instruction in the code with the following restrictions. The first argument, I mean, the Bootstrap specifier has to be a constant, also the invocation name, and there is no restriction on the arguments. In the Indy case, we have static arguments which are represented in the Bootstrap specifier parameter, and we have also dynamic arguments. So this is a quick definition of the Bootstrap specifier class. No, it's simple. It's just a method handle with some static arguments that has to be constant, as mentioned. So we're going again to an example we have seen before in the presentation. So here we have a class constant, and we are explicitly calling the LDC methods in the intrinsic class. Sorry. And this is the generated code. As we can see, there is an LDC actually in the bytecode. No? So it's very handy to expose the LDC, and what you see is what you get. No? In this case, sorry. So somehow the code before the LDC is redundant in this case. Actually, in previous versions of the project, we were just generating the LDC, and I mean that could actually decrease the volume of the bytecode. But it was decided to be less magic and to actually represent what code was happening. But I wondered that it could be interesting for some people to actually go directly to the LDC. So this is an example of the use of Indy in the source code. This is very similar to the first example, which is making use of string concats. In the first sample, we were using reflection. Here, we are using the InvokeDynamic intrinsics. We can say that the code is kind of similar in complexity, but before we were not actually generating the InvokeDynamic. Here, the compiler is actually generating the InvokeDynamic. Could this be simpler? We were exploring ways to simplify the code even more, and we are working on that. But the thing here is that you get the real thing. I mean, once you go to the bytecode, you actually see the InvokeDynamic there. I mean, without having to spin the bytecode, etc. So this is really powerful. I mean, and something that, of course, we couldn't offer to Java programmers before. So we got to a point where we have all of these. We have several consoles with methods with the annotation to inform the compiler to track some of those methods. So what now if I need to add a new console method? What if I need to add a new factory or a totally new console? I mean, do I need to change the compiler? Well, the idea is no. I mean, the answer is no. Using the annotation, you can inform the compiler, please track the result of this method and make sure that any argument to this method is actually a constant expression. For example, this method doesn't exist in the API. It's something I make up, and but just adding this interface and API and adding the trackable constant annotation will be enough for it to work, without adding any other modification to the compiler. Okay, this part seems easy, but what about code generation? Suppose a new console is added. Not that we want to support it, but let's suppose that a new console is added, or just an existing constant is renamed, which would be exactly the same effect. So, do I need to change the compiler? Well, there is an understanding between the Java C and consoles, and we have provided an API so that when the compiler doesn't know how to write a constant to the constant pool, it asks the constant to write itself to the constant pool. This is very handy, and it kind of closes the circle. So it's easy to modify consoles, rename them, whatever, without actually having to modify one line of code in the compiler. And so this is the part of consoles, and Paul, if you want to make the summary.
I can just, I'm not going to read the slide there, it just summarizes what we just said, tell them what you told them. The interesting thing is it's really foundational technology I think we can use to build other stuff on top of and remove the limitations we currently have, both at the VM level and the language level. And I think that's going to sort of open up things, not just for us, but for other people if we do this right. I think the API is going to have to go for another couple of rounds of the API grinder review. I think that's good. And now it's there for people to use. I encourage people to go and do that. We want feedback on this. And at the moment, it's very low level. There could be a bunch of different levels depending on how much sort of initialization you might want to do with things. There could be fluent APIs. We haven't really explored that. Maybe that's a good area as well. But also, a nice thing about this project is it's a nice vertical over the whole Java runtime, and that's what I love about this. There's a bit in Java C, there's a bit in core libraries, and Java C interacts with core libraries through reflective calls. That really surprised me. The core libraries interacts with the VM and up call. It's like a holistic piece of functionality in the whole Java runtime, and that's a really, to me, that if you can get that right, that's a really solid project, and a lot of the projects we do are around that holistic value. I'd like to see more of that. Okay.
Yeah, I think this is the first time that we have that kind of interaction between the compiler and the libraries.
Yeah.
Kind of during the compilation, invoking, effectively invoking a method and getting the result and affecting the compiler, the result of the compilation with that. No?
Yeah.
Yeah, that was very interesting.
Okay. So there's a workshop afterwards on Java Lang Invoke where we can take questions. I don't know what the time, are we running out of time? We have a few minutes for questions.
We're on break next, so.
Okay. Let's take some questions now and we can flow over with more. So.
Get a microphone.
How many times before people realize that it's a macro system?
Yeah.
Already happened.
All right. You just realized it was, but now. At least
no,
twice.
Before. But, and what about recursion?
Recursion at the VM, the Condi level, or the language level?
When the compiler will call some code that do infinite recursion. And
I think
like
do you know more about that?
Yeah, it would be nice to have an example of that. No, I think that there should be. We can enforce ways to fix that. To avoid that. No, but right now I don't see any.
I think it's the same as with Indy, right? An Indy Bootstrap can go walkabout, and this is just another kind of Bootstrap that can be upcalled from your doctor.
When the compiler call as an arbitrary method and
Yeah, it's contained, as it
Yeah.
were, so it can't leak out.
So I've been the first guinea pig to be using this stuff. So I just want to make a couple of comments about what this is good for. So there are two really big advantages that come out of this. One is, how many people here have written Indy Bootstraps before? Right? It's kind of like programming with boxing gloves, right? You're really limited to the types you can use. This makes Indy programming a lot more like regular Java programming. So your bootstraps can be more expressive, and it also means that they're going to be more likely to be binary compatible. And then the other thing, the other hidden benefit of this is it allows us to move even more computation from invocation time to link time. So the range of things that we can describe as VM constants and get lazy initialization from the VM load constant mechanism grows hugely, and it's each time you think, oh, okay, I found all the constants in my code. No, there's a whole other wave of things that can, once you've made this stuff constant, you can make more stuff constant based on that. It's really, it's quite nice. So compiler writers will really like this.
I'd like to just inject into that as well. It might help us break cycles at Bootstrap, more laziness there in a more formal way than having to put stuff in inner static classes and so forth like that, which help us rearrange our Bootstrap code and get faster startup too.
Especially if you can attach a constant pool reference to a Condi constant to a static final constant, and then treat that specially with lazy semantics. Brian was just being very modest. This whole thing of constable thing is, I think, his brainchild, because I remember him looking at my Indify code and just vomiting all over it, quite justly. and saying, surely we can do better than this. And so he embarked on a multi-year quest to surely find what could be better.
Yeah, I think, John, you told me that this Indify test irritated Brian so much, it caused him to sort of start thinking about this.
Yeah, that's one thing that that probably I didn't stress during the presentation. Is going to be open to create, I mean, new consoles for free. So it will be limited to some methods in the API in the JDK.
Just in terms of API, I think you can get rid of the interface constable. Basically, what you want is a kind of serialization. You can do that with an annotation. And you can retrofit string, method type, and so on by attaching this annotation.
Yeah, I mean, yeah, I would like to work on an example and see and try to break it, try to make it fail because of this. It would be interesting.